What you see here is a two-storied, four-flat apartment building constructed recently in the Sylvan campus of IIT Madras. From the outside, it looks like any other conventional building. So, what's special about this? It has been built much faster than conventional buildings. In just 1 month, it demonstrates the use of a green alternative technology, making use of industrial waste gypsum and glass fibers in the hollow panels called GFRG panels, glass fiber reinforced gypsum panels. This building, which does not need any plastering, uses much less cement, sand, steel and water than conventional buildings. So for the same carpet area, the built-up area and the building footprint is much less than conventional buildings. Buildings up to 8 stories can be designed using this load-bearing system without the need for any beams and columns. In summary, the construction is rapid, cost-effective and green.
Providing affordable housing is a formidable challenge in India. Our faculty and students have been working tirelessly on this for nearly a decade. And today, we have a technology which provides affordable and, more importantly, rapid housing using some very novel ideas. The technology results in enormous savings in almost all materials which are considered today to be environmentally sensitive, such as water, sand, bricks and steel. At the same time, it uses a benign material which is a waste product of fertilizer manufacture and is available in plenty.
What you see here is the stock of waste gypsum, 7 million tons of it, with an addition of 2,000 tons every day piled up into a hill awaiting disposal. It is this waste product of the fertilizer industry reprocessed by calcining to make gypsum plaster that forms the raw material for the GFRG panel. The panels manufactured at RCF Mumbai and FACT Cochin are based on the technology transferred through collaboration with Rapid Wall Building Systems Australia.
Big advantage of gypsum is that it has an initial setting time which is about half an hour. So in the factory we can pour a panel and half an hour later we can put it on the forklift and take it off the machine. So if we would design this panel in concrete, we could make one per day, and now we can make one per hour.
The panels are cast in 3 stages on a special table by pouring a paste of calcined gypsum and other chemical additives. Glass fibers are spread evenly onto the mix by means of a screeding and rolling process. Next, special aluminium plugs are inserted on top of the finished first layer with 20 mm gaps in between to form the hollow cavities in the panel. Now, the second pouring of the mix is done along with cut glass fibers with tamping to form the ribs of the hollow panel. In the third stage, the process of the first stage is repeated to complete the top layer of the panel. After setting, which takes 25 minutes, the plugs are withdrawn and the casting table is rotated, and in its vertical position, the panel is taken out for drying by means of a special forklift. The drying of the panels is done in a dryer chamber in which hot air is circulated to dry the panel evenly for 90 minutes. After drying, the panels are cut using a computer-aided and automated process tailor-made to the specified requirements for any building project. It is important that all this information is carefully planned in advance and furnished at the plant site by means of cutting drawings to be furnished by the architect or engineer. The original rapid wall technology developed in Australia aimed at the use of these panels only as vertical walls, subject primarily to gravity loads. IIT Madras extended the use of the GFRG panels also as the floor slabs and staircases, enabling the use of GFRG panels for the entire building system and minimizing the use of reinforced concrete.
We really felt that this material has a great potential for use in countries like India. And we also explored potentials that I think the Australians had not utilized. So we realized that the same panel, which is 12 meter long as manufactured in the factory and 3 meter height, can be also used as a floor, as a slab. If you design it properly and reinforce it properly and fill the cavities with concrete. So you have small micro T-beams in the slab. Then we said the whole thing can be used as a building system with especially the joints also concreted with reinforced concrete.
The cut panels are then loaded onto trucks, keeping them in a vertical position using stillages so as to avoid any damage during transportation. We now see these trucks arriving at the IIT Madras campus and reaching the construction site. The foundation for the building is conventional in nature, requiring setting out and excavation up to depth of 1 meter below ground level. A levelling course of plain cement concrete is laid over the trenches and is subsequently waterproofed over the entire exposed surface. A conventional footing is constructed using fly ash blocks with a coat of waterproofing sprayed on all sides aimed at preventing capillary rise of any water into the building. A concrete plinth beam with reinforcing steel is cast on top of the fly ash blockwork. Vertical bars called starter bars are positioned inside the plinth beam to match with some of the cavities of the GFRG wall panels. The entire foundation construction took 11 days in this demo building. Next, the superstructure work is taken up. To ensure adequate structural safety of the building, a proper structural design is needed.
If you want to have a building system, there is a process you have to go through, especially if you wanted to certify as a building material. One is there are certain types of tests you have to do. For example, water absorption, and then you also have to see the strength when it is in water and outside the water, how it is going to perform. And there are a lot of other functional tests also you have to do. Initially, when the Australians thought about this particular system, they only used for vertical loads. Vertical loads means it takes only gravity loads due to its own weight, building's weight. What is important in our situation, in our country like ours, we also have a large amount of earthquakes that can potentially happen. So we have to be very careful in understanding the building system's behavior when it is subject to lateral loads due to earthquake. Okay. So one of our PhD students, he has done that work. We simulated those tests, and we arrived at a particular design procedure which is novel and which is slightly different from what we conventionally do for reinforced concrete shear walls. Because here you have GFRG hollow things and you fill with concrete. And when you fill with concrete, it is not likely you may not get good bond between the concrete and the wall surface, the GFRG that you have. But beauty is, as long as you put them together, you connect them and you make them into a unit, actually lack of bond also is advantageous because there will be loss of energy. Energy can be dissipated through fraying of the surfaces. And it also a little more flexible. So all those things also would help you in the earthquake performance of this building system.
Based on extensive research carried out by IIT Madras, a structural design manual has been prepared and published by the Building Materials Technology Promotion Council BMTPC, Government of India.
This work has been recognized by the BMTPC, Building Materials and Technology Promotion Council of India. The Department of Science and Technology came forward and actually offered us a generous grant to complete the R&D work and bring it to a stage of technology transfer.
Further, IIT Madras has developed earthquake-resistant design procedures for use in different seismic zones in the country. 4 PhD research scholars at IIT Madras have contributed to the R&D work since 2004. On the first day of the superstructure construction, the wall panels are erected with the help of a crane. A special locking system is used to grip the ribs of the panel on top, enabling easy lifting without any damage to the panel. The panels are hoisted vertically and positioned in place over the starter bars jutting out from the plinth beam. Then, appropriate reinforcement bars are inserted as per the design into the cavities. In this two-storied building, every third cavity is required to be filled with concrete and reinforced with a 10 mm bar. Other cavities can be filled with any inert material such as quarry dust mixed with 5% cement and water. The vertical steel bars are tied to the starter bars and the verticality of the panel is ensured by using the plumb bob. Grooves are cut into the edges of the panel to facilitate integral bonding with adjoining panels. It is mandatory that all joints between connecting panels are filled with concrete and suitably reinforced with steel. The entire ground floor wall panel erection is completed in 4 days. The door and window frames are then fixed in position at their respective locations where the panels are cut. The staircase work is also taken up using GFRG panels as the waist and landing slabs with reinforcement bars in all the cavities. Shuttering for sunshades is also put in place along with reinforcement bars. Next, the work of casting the first floor slab is taken up. Instead of a conventional solid concrete floor slab, which is typically 100 to 125 mm thick, the GFRG panels are used. They are placed horizontally over the walls in different rooms. The ribs typically spanning along the shorter direction. Concrete tie beams connect the panels to the walls at all junctions. Every third cavity in the horizontal GFRG panel is cut open from the top and a reinforcement cage inserted to serve as a concealed beam. Further, a steel welded mesh is placed on top of the entire floor slab and is subsequently embedded in a screed of concrete 50 mm thick. The advantage with the system over conventional concrete slabs is that there is no need for shuttering and the finish at the bottom is excellent, not requiring any plastering. Also, the propping required from below at the time of concreting is minimal. Conduits for electrical work are kept in place before concreting the slab. After completion of the entire concreting in the floor slab, including the balconies and the staircases, the panel erection for the walls in the next floor is taken up and rapidly completed. Then, the GFRG panels in the roof slab are put in place along with the reinforcement at various locations.
So today is an important day. We are going to cast the entire roof in one go. So we are trying to make sure that everything is put in place, the reinforcement for the balcony portion, for the staircase, and the entire roof will be done, the concreting will be done today in just one day. As you can see, all the conduits have been put in place, the plumbing has been put in place. We have every third cavity with an embedded beam, and we have a screed on top with this welded wire fabric. The minimum thickness of the screed is 50 mm, but in the interest of draining the rainwater on the roof, we are laying down a slope, so it's 75 mm on the front side to 50 mm on the rear side, so that there's a natural slope in the roof. And you also have this concrete being filled in every third cavity in the walls, all the way from the second floor to the first floor to the plinth beam. So that's what gives the integrity to the structure. That's the reinforcement present in these cavities, provided with the required resistance to lateral loads such as earthquakes. This is just a two-storied building, so there's not much problem here. But the same principles and the same concepts can be used for multi-storied buildings all the way to 8 or 10 stories. And while they are working on the concrete, another team is working on putting the reinforcement cages in place, putting the fittings for plumbing in place, putting the conduits in place. So it's going to move from that end to this end, and by the end of the day today, it'll all be over. Thank you.
A 5-course waterproofing of the roof is done subsequently to ensure complete and long-term protection against any possible leakage. It is proposed to test the effectiveness of this waterproofing technology by filling the roof with water 200 mm high and retaining the water for 7 days. Other load tests are also planned in the floor and roof slabs of this GFRG demo building to assess and ensure adequate structural performance.
You need a team which can handle the panels and put it in place. You need a team which can cut openings in them and place the reinforcement wherever required in place. You need a team that can do the concreting. So certainly it will help to have specialists who work closely coordinated.
Especially building services also.
And you have to put the building services in time, the plumbing and the electrification. So if a company does this in that organized manner, then that would be the ideal thing.
Let us now go inside the building and look at the finished interiors.
We believe that this technology has the potential for helping India meet the challenge of providing housing for its millions in the shortest possible time.